Hello everyone. Today we are going to discuss oscillations NCERT questions. So let's start with the first question. The question says that which of the following example represents periodic motion? So in this question we are being asked about periodic motion. We know a motion that is repetitive and that repeats at regular interval of time is known as periodic motion. So we will have to check with all the four options that whether they are repetitive or not, and if they are repetitive then are they repeating at regular interval of time or not. So the first option is a swimmer completing one return trip from one bank of the river to the other bank. So this motion is repetitive, but we don't know whether the swimmer is taking equal interval of time or not, so we can't say that the motion is periodic. The second option is a freely suspended bar magnet from its north-south direction and released. So the nature of motion here is when displaced from its equilibrium position, north-south direction, the bar magnet will oscillate and back and forth around its direction due to the restoring torque from the Earth's magnetic field. So we can say that it is a periodic motion, and the motions are periodic because the magnetic field repeatedly swings back and forth around the equilibrium position. So here the Earth's magnetic field will provide the restoring torque. That's why the motion will be periodic. The third option is a hydrogen molecule rotating about its center of mass. So here again the nature of motion, when we talk about nature of motion, the hydrogen molecule rotating about its center of mass is a rotational motion, and yes, it is periodic because it's complete one full rotation and continues to rotate in the repeating cycle. And the fourth option is an arrow released from a bow. So this motion is not at all a periodic motion, because once the arrow leaves the bow it never returns back, so it is not a repetitive motion. We can't call it a repetitive motion. So let's proceed with the second question. Here we have got, the question says which of the following examples represent simple harmonic motion and which represent periodic but not simple harmonic motion. So here difference between simple harmonic motion and periodic motion is, in a periodic motion the motion just repeats at regular interval of time, but in simple harmonic motion the restoring force is there, which is restoring force MA is proportional to minus x, that is in the opposite direction of motion. So when the restoring force is in the opposite direction of motion, then only we can say the motion is simple harmonic. So let's proceed discussing the four options. The first option is the rotation of Earth about its axis. So here when we talk about the nature of motion, the rotation of Earth is a periodic motion with a period of 24 hours, but it is not simple harmonic motion because it does not involve restoring force which is proportional to displacement. So we can't say that it is a SHM, but it is a periodic motion. The second option is motion of an oscillating mercury column in a U-tube. So the motion of mercury column in a U-tube. So the question is generally basically asking that there is an U-tube and inside it there is mercury which is at equilibrium. Now if we push one of the column of mercury with some distance and then we will release it, then will it be oscillating with a simple harmonic motion or not? So yes, the restoring force is proportional to negative direction of displacement, so we can say that the motion is simple harmonic. Third option is motion of a ball bearing inside the smooth curved ball when the ball is released. Here the ball bearing oscillates back and forth around the lowest point of the ball, so the motion is periodic. And when we want to check about its simple harmonic nature, Then when the ball is released from the top position, then it is having maximum potential energy, which is converted into kinetic energy when it is at the base, and then again the base is it translates to potential energy as it reach on the top position from the other side. Now if we neglect the frictional force, as it is mentioned over here that the ball bearing is nearly frictionless, and the ball is also very smooth, so we can neglect here the friction force, so we can say that the simple harmonic motion is there. Now the fourth option is general vibration of a polyatomic molecule about its equilibrium position. So the vibration of polyatomic molecule involve movement of atoms about their equilibrium position. These vibrations can include various modes and frequencies, so altogether this motion can't be termed as simple harmonic, but individual motions are. So we can't say that it is a simple harmonic motion, but it is periodic. So let's move to the next question. Here the question is saying that below figure depicts 4 plots, x and t plots for linear motion of a particle. Which of the plots represents periodic motion, and what is the period of motion in case of periodic motion? So periodic motion is a motion that repeats itself at regular interval of time. So upon visualizing we can make a better guess. Here the plot is, the position x is exponentially increasing and it is not going in the opposite direction, so it is not repetitive at all, so we cannot say that it is a periodic motion. In the plot B, we see that there is a repetition at regular interval of time and with the time period of 2 seconds, so it is a repetitive motion and it is periodic also because the period of motion is fixed, so we can say that it is a periodic motion. In the third plot, it is very irregular motion and it is not repeating at regular interval of time, so we can't say that it is a periodic motion. The fourth option as well, this represents a sinusoidal type of graph which is repetitive and also it is repeating at regular interval of time of 2 seconds, so we can say that it is a periodic motion. So let's proceed to the next question. So here in this question we have to find out which of the following function of time represents simple harmonic periodic but not simple harmonic and non-periodic motion. Give period for each case of periodic motion. Omega is any positive constant. So here we have to find out whether they are simple harmonic motion, whether it is periodic but not simple harmonic motion, and or are they non-periodic motion. So we know that for periodic motion, so all these functions are given a time function. So the time function of simple harmonic motion, we know that it is represented in the general form of a sine omega t plus phi plus minus phi, or a cos omega t plus minus phi. This is the function for displacement in the time format. So if the option will resemble this form of function, then we can say that it is a simple harmonic motion, or we will find the period, then we can say whether it is periodic motion or none at all. So the first option is sine omega t minus cos omega t. Here we can use the trigonometric identity sine a minus sine b, and which can be later written as 2 sine a minus b by 2 multiplied by cos a plus b by 2, which is equals to root 2 sine omega t minus pi by 4, which is of the form of a sine omega t plus minus phi. So we can say that it is a simple harmonic motion with the time period of 2 pi by omega. Now in option number B, we have sine cube omega t. Now sine cube omega t is equals to 3 sine omega t minus 3 sine 3 omega t. So again we see here that there are two frequencies. The first part is having 2 pi by omega and the second part is having 2 pi by 3 omega. Now this is the sum of sine functions with different frequencies, indicating that it is periodic motion but not simple harmonic motion. Now if it is a periodic motion, then what is the period of this motion? In order to find out the period of motion, whichever function has the larger period, so we can say that the period of motion of this entire function is that period. Now the third option is 3 cos pi by 4 minus 2 omega t. Now again it is of the form of a cos omega t minus phi, so we can say that it is simple harmonic motion with the time period of pi by omega. Now in fourth option we have 3 cosine functions in addition format. So again they all have different frequencies, so they are periodic but they are not simple harmonic in nature because we can't represent them as a single frequency. So we will say that it is a periodic motion but not simple harmonic motion. Now in fourth option it is not periodic at all because it is exponentially it is an exponential function. It increases monotonically, so we can't say that it is periodic at all. And fourth option also it increases with time, so we can't say that it is a periodic motion at all. Now let's move to the next question. The question says that a particle is in linear simple harmonic motion between 2 points A and B 10 centimeter apart. Take the direction from A to B as positive direction and give the sign of velocity, acceleration and force on the particle when it is. So there are 6 positions that is given, and we have to find out the direction of the velocity, the sign of velocity, acceleration and force. Now here we can say that whatever the direction of acceleration will be, the same direction will follow the force, because force is mass times acceleration, so acceleration and force will have same direction. And let's now consider all these 6 directions and find out what is the sign of velocity and acceleration. So when the particle is at A, now the particle is moving between A and B, so A and B are the extreme positions. So when the particle is at A, its velocity is 0 because it is at extreme position, and it is about to go to the mean position, that is O. So its acceleration or force will be towards the mean position or in the positive direction of velocity. So we can say that the acceleration and force will be positive and velocity is going to be 0. Now when the particle is at end of B, the end B, again it is an extreme position, again we can say that velocity is 0 and acceleration is in the negative x direction. Similarly the force is also in the negative x direction. Now the third option is at the midway between A and B going towards A. Now when the position of the particle is at the midpoint, then and it is going towards A, that is it is moving in the negative direction of the x-axis, so its velocity is going to be negative because it is moving in the negative direction. And since the motion is retarding because the deceleration force is acting with the magnitude of minus of kx, so the force will be in the positive direction. So again velocity is negative and force and acceleration are in the positive direction. Now in the fourth option we have when the object is at 2 centimeter away from B going towards A. So it is not at the extreme position B, but it is moving towards A. So here it is in the positive x direction. Now it is moving towards, since it is moving towards A, so its velocity is in the negative direction, and its force and acceleration will be directed towards the negative x direction, so it is going to be negative. Now in E we have at 3 centimeter away from A going towards B. So again it is in the it is somewhere in between A and O, which is A is the extreme position and O is the midpoint, and O is the mean position, and it is moving towards B. So it is moving towards the positive direction, so its velocity is going to be positive, and its force and acceleration is also going to be positive because it is moving away from A, so it would be accelerating till it reaches the mean position. At mean position, force and acceleration is going to be 0. Now with the F option, we have at 4 centimeter away from B, going towards A. Now 4 centimeter is the 4 centimeter away from B is between position O and B, and it is moving towards A. So it's obviously its velocity is going to be negative, and its acceleration is also going to be negative, because since it is approaching mean position, so and it is in the positive direction, so its acceleration and force will follow the negative direction. Now let's move towards question number 6. So question number 6 says which of the following relationships between acceleration A and the displacement x of the particle involve simple harmonic motion? So the acceleration, we know that force law for simple harmonic motion is in the displacement form is F equals to minus kx, or acceleration is proportional to a negative of displacement, or in the negative direction of displacement. So whichever function will follow these rule will have, we can say that the particle will involve the simple harmonic motion. So here in option A, we have a positive x, the acceleration is increasing linearly with x, so it can't be simple harmonic motion. And in option B, we have minus of x square. Again, whether x is positive or negative, it is going to be minus, so force never changes its direction, so again it is not a simple harmonic motion. And option C, we have minus of 10x. Again, this is linearly decreasing, so it can't be, so no, it is not linearly decreasing, actually it is minus of x. So when x is negative, the force is positive, and when x is positive, then force is in the negative direction, so we can say that it is exhibiting the simple harmonic motion. And in option D, we have odd number of power of x, so we can say that the force will be retarding in nature, but it will not be simple harmonic motion, it will be harmonic motion of higher order, so it can't be simple harmonic motion. So let's go to next question, that is question number 7. So here in this question, we have a motion of particle executing simple harmonic motion is described by the displacement function xt equals to a cos omega t plus phi. If initial t equal to 0 position of the particle is 1 centimeter and initial velocity is omega centimeter per second, what is its amplitude and initial phase angle? The angular frequency of the particle is pi per second, that is omega is equal to pi per second. And if instead of cosine function we choose the sine function to describe the SHM, x equals to b in the form of x equals to b sine omega t plus alpha, what is the amplitude and initial phase angle of the as in the above condition? So we have been given that the initial position of the particle is 1 centimeter and initial velocity is omega centimeter per second. We have to find out initial phase angle and the amplitude. So with the information, with the given general form of simple harmonic motion as cosine function, we have to at first use cosine function. So we will use a cos omega t plus phi. Now we have been given that at t equals to 0, the value of x at t equals to 0 is 1 centimeter. So we can write it as x at 0 is equals to a cos phi equals to 1. So cos phi is equals to 1 divided by amplitude. A is the amplitude. Now when we differentiate it to find the velocity, x dash rho equals to omega centimeter per second, it is given. So when we differentiate a cos omega t plus phi, then we will get minus of a omega sine phi. Now from this equation we will get sine phi as minus of 1 by a. So using the identity cos square phi plus sin square phi equals to 1, we will simply square these two terms cos phi and sin phi and add it. So 1 by a square plus minus 1 by a whole square is equals to 1. So a will be equal to root 2, and here a was our amplitude. So we have found our amplitude. Now once we have found our amplitude, we can solve the either equations, that is this equation or this equation, this cos phi equals to 1 by a. substituting a, then we will get phi equals to pi by 4, and using this sine phi equals to minus 1 by a, we will get phi equals to minus pi by 4. Now we know that phi with the changing angle, sine and cosine have different signs. Now we can say that when phi equals to minus pi by 4, here sine is negative and cos is positive, and we have a positive equation over here. So phi is in the fourth quadrant, or we can say phi equals to 7 pi by 4 or minus pi by 4. So so the equation of simple harmonic motion is going to be xt equals to root 2 cos omega t minus pi by 4, or root 2 cos omega t plus 7 pi by 4. Here root 2 is the amplitude. Now we have to, the second part of the question said that we have to write this function in the form of sine function, that is x as a function of b sine omega t plus alpha. So we will have to find out the value of b, and also we have to find out the value of omega, and will it change or not. So let's now turn this function into a sine function. So xt equals to b sine omega t plus alpha. Now x at t equal to 0, it would be equal to b sine alpha, that is equals to 1 centimeter. We have been given that at x t equal to 0, it is 1 centimeter. So again sine alpha is going to be 1 by b. Now similarly we did in the first part of the question, we will differentiate it, and we found out that b is equals to root 2. So amplitude is not changing, amplitude is same. Now using third equation, that is sine alpha is equals to 1 by b, we will get alpha equals to pi by 4 and cos alpha equal to 1 by root 2 as well. So alpha is equals to pi by 4. Here the phi is in first quadrant. Now x as a function of t is equals to root 2 sine omega t plus phi. So only the change in cosine and sine function is that of the phase angle. Amplitude and frequency remains same, that is frequency, angular frequency omega is same. So we can say that only the phase angle has changed. There in cos it was minus pi by 4, and in the form of sine it is plus pi by 4. Let's move to the next question. If you have any doubt, then you can ask right now. I will take a break of 5 minutes. The question says that a spring balance has a scale that reads from 0 to 50 kg. The length of the scale is 20 centimeter. A body suspended from this balance when displaced and released oscillates with the period of 0.6 second. What is the weight of the body? So here we have to find out the weight of the body, and given that the for 50 kg the displacement is 0.2 meter. So we will balance here the force. So the force will be equal to the weight of the body, and we know that spring force is given by K multiplied by X, where K is the spring constant and X is the displacement from the natural position. So here K times 0.2 meter would be equal to 50 times the acceleration due to gravity. So we will find out the value of K as 2450 Newton per meter. Now we know for the time period of spring mass, oscillating spring mass, T is given as 2 pi times under root mass divided by the spring constant. So T would be equal to 0.6 second. Now once we have got the time period, we also need to find the weight of the body given the time period is 0.6 seconds. So given T equals to 0.6 second, we know that the time formula for T, that is the time period in the case of spring balance, it is 2 pi times under root m by k. Here m is the mass of the body by k. Now for this mass that is being weighed, time period is 0.6, and we know the value of k, so we can easily find out the value of m. Now finding the value of m, we get 22.34 kg, or it can be written as 218.93 Newton. So let's move to the next question. So in this question, it is given that a spring having with the spring constant 1200 Newton per meter is mounted on the horizontal table as shown in figure 13.9. It is mounted on the horizontal table. The mass of 3 kg is attached to the free end of the spring like this. This blue mass is 3 kg. The mass is then pulled sideways to a distance of 2 centimeter and released. Now it is displaced by 2 centimeter and it is released. So we have to determine the frequency of the oscillations. We have to determine frequency of the oscillation, and also we have to determine the maximum acceleration of the mass, and we have to determine the maximum speed of the mass. So for determining the frequency of the oscillations, we know omega is equals to under root k by m, because omega, that is the angular frequency of oscillation, is given by, for the spring balance it is given by under root k by m, and omega we also know that it is equals to 2 pi by t. So if we equate these two things, we will get the time period of the oscillation, or we can get the frequency. If 1 by time period is known as the frequency, so 1 by time period of frequency would be equal to 1 by 2 pi times root under k by m, where k is given, m is also given, and x max is also given. So we only need for the calculation of frequency, we only need k and m. So we will substitute in this equation and we'll get the frequency. Now for acceleration maximum, we know that it is in the, since the equation is in displacement form, so we can get the maximum acceleration as omega square a. Now a is the maximum amplitude, that is 0.02 meter. So when we multiply omega square in times a, then we will get the acceleration maximum, that is 8 meter per second square. Now V max is given by omega times a, that is the amplitude. So again V max would be equal to 20 times 0.02, that is 4 meter per second. 0.4 meter per second. So let's move to the next question. Here in this question, it is referring to the previous question. In exercise 13.9, let us take the position of mass when the spring is unstressed at x equals to 0 and the direction from left to right as the positive direction of the x-axis. Give x as a function of time t for oscillating mass. If at the moment we start the stopwatch t equals to 0, the mass is at the mean position, and the mass is at the maximum stretched position, and the mass is at the maximum compressed position. In what way do these functions for SHM differ from each other? and in frequency, amplitude, or an initial phase. So we have been given the initial state of the mass, that is unstretched at x equals to 0. So and also we have to find the functions, time functions for this SHM, and we have to find out whether in all these three cases we have to compare for the frequency and amplitude or the phase, what will change. So let's start making equation for each of these initial conditions. So the first initial condition is mean position, and also the question is referring to the previous example in which we get the data of omega is equals to 20 radians per second and acceleration maximum, that is omega square times a equals to 8 meter per second square and omega times a equals to 0.4 meter per second. So at mean position x at t equals to 0 is 0. So taking the function of SHM as xt equals to a sin omega t plus minus phi. Here at t equals to 0, x equals to 0. So here phi must be equal to 0, so that sin 0 is equals to 0. Now at xt equals to 0, sin a sin of 0 degree would be equal to 0. So the equation will be of this form, that is 2 that is a sin omega t, here omega is 20, so it would be equal to 2 sin 20t. Now in the B, when initially the block is at the maximum stretched position, so x naught would be equal to a, that is 2 centimeter away from the mean position. So xt would be equal to a cos omega t. Now let's assume that the function of SHM would be equal to a cos omega t. Now phi we have taken a cos omega t, so that at t equals to 0 we won't get into the mess of the phi, that is the phase constant. So it would be equal to 2 cos 20t. We can also interchange into sine and cosine form using trigonometric identity. Now in the third option, it is at maximum compressed position, initial x is equals to minus of a. Now let us assume the position, the function for this SHM would be equal to a cos omega t. Now it is given that at t equals to 0, the position of x is minus a. So at x equals to 2, we can write minus a cos omega t. So it would be x of t is equals to minus of 2 cos 20t. Now here we see that omega, that is the angular frequency, never changed. So it is going to be equal to, it is going to be constant. Only the thing that has changed is the phase angle. Amplitude is also same. So we can say that in all these three conditions, only the phase angle is changing and the amplitude and its frequency remains unchanged. Let's move to the next question. Here in this question we have figures 13.20 corresponds to two circular motions, the radius of the circle, the period of revolution, and the initial position of the sense of revolution, that is the clockwise and anti-clockwise, are indicated in each figure. Obtain corresponding simple harmonic motions of x projection of radius vector in the revolving particle p in each case. So here we have to write the x projection, and the particle is moving in the circular motion in both A and B format, in A and B figure. So for figure A, since we have to write it in the x projection, we have been given the information. We can take it from the figure as a equals to 3 centimeter, that is the maximum amplitude is 3 centimeter, and the time period of 2 seconds is given, and omega we can find it from the time period, and that is equals to 2 pi by t, or it is equals to pi. So at t equals to 0, it is in the mean position. The projection of particle p on the x-axis is at the origin, so we can say that at t equals to 0, x equals to 0. So x at t is equals to 3 sin pi t. Here we can see that at t equals to 0, sine will go to 0, so xt can be written as 3 sin pi t. Now in second figure we have x projection, the particle is initially at the extreme position in the left side. So we can say that the initial position of the particle is minus of a, or amplitude here is 2 meter. So the x at time t equals to 0 is going to be minus 2 meter. Now the convenient equation for this format would be a cos omega t, because cos at 0 is equals to 1. Now since initially it is at minus of 2 meter, so we can write it as minus of a cos omega t, and the value of a would be equal to 2 meter. So the position time equation for this case would be equal to minus 2 cos pi by 2 t. As in the general case, when the projection of when we have to write the equation for equation of SHM for the projection of x, we should always use cos function, and if we have to write the equation of SHM in the y-axis, we should only use the sine function. We should always use the sine function as it is more convenient. Now this question says that plot the corresponding reference circle for each of the following simple harmonic motions. Indicate the initial t equals to 0, initial position of the particle, radius of the circle, and angular speed of the rotation of the particle. For simplicity, the sense of rotation may be fixed to be anti-clockwise in each case. X is in centimeter and t is in seconds. So here we have to plot all these 4 cases. The first is x equals to minus sine 3t plus pi by 3. So here we can extract the information that is needed for plotting the graph, plotting the path of the particle. So here amplitude, we can find out the amplitude by correlating this in the form of a minus of a sine omega t plus phi. So here a is equals to 2 and displacement it is in centimeters, so the radius of the circle is going to be 2 centimeter. And at t equals to 0, if we substitute t equals to 0, the position of the particle would be minus of 2 sine pi by 3, and pi by 3 is equals to root 3 by 2. So the position of particle, we have to find it on the circle. So since we found, I told you that whenever the projection of x has to be plotted, the convenient form to take is the cosine format. So when we convert this into the cosine format, it would be equal minus sine is equals to cos pi by 2 plus phi. Here theta is equals to pi by 3. So if we add pi by 2 plus theta, it would give us 5 pi by 6. So the theta and from the positive direction of x-axis, the angle would be equals to 5 pi by 6, and omega is equals to 3 since omega won't change in trigonometric conversions. So the equation of motion would be 2 cos 3t plus 5 pi by 6. Now the second equation is x equals to cos pi by 6 minus t. Here already it is written in the form of cos format. So we can here see that x at t equals to cos pi by 6 minus t. So cos minus theta is equals to cos theta, we know from the trigonometric identity. So we have we can write cos pi by 6 minus t as cos t minus pi by 6. So at t equals to 0, the particle is at minus pi by 6 position, so that is here, and amplitude is 1, so it would be 1 centimeter. Now simply we can write the coefficient of t as omega, and that omega angular frequency is 1 radians per second. Now in third plot we have 3 sine 2 pi by t plus pi by 4. So again let's turn this into the cosine format. So we know that sine pi by 2 plus theta is equals to cos theta. So it would be equal to 3 cos 2 pi t minus pi by 4. Here initial phase is again pi by 4 and initial is clockwise direction, or in anti-clockwise direction you can find out using 2 pi minus pi by 4. So amplitude is the coefficient of this cosine function, that is 3, and x naught position is at t equals to 0, that is cos minus of pi by 4, that would be equal to 3 by root 2, and omega is 2 radians per second, that is the 2 pi radians per second, that is the coefficient of t. In the fourth plot, it is given that 2 cos pi t. It is a simple equation without any initial phase angle, that is phi. So at t equals to 0, the position of x equals to 2 centimeter, or the axis. So A would be equal to, the amplitude would be equal to 2 centimeter, and omega would be equal to pi radian per second, and x naught equals to 2 centimeter. Now let's move to the next question. This question we have been given that figure 13.21 shows the spring of force constant K clamped rigidly at one end and mass m is attached to its free end. Force applied at the free end and stretches the spring. Figure 13.21 shows the same spring with both ends free and attached to a mass m at either end. Each end of the spring in figure 13.21b is stretched by the same amount of force. What is the maximum extension of the spring in two cases? So the A part of the question asks that what is the maximum extension in the spring in two cases, and B part of the question asks that if the mass in spring in figure A and two mass in figure B are released, what is the period of oscillation in each case? So here figure A is very simple. We know the equation for a time period of oscillation in the case of simple spring, that is t equals to 2 pi root under m by k. But in B, the effective mass comes into play because it is a system of two mass, both of mass m, and they are oscillating together. So effective mass is given as the product of two masses divided by summation of those mass. So the effective mass would be equal to m by 2. So in this equation, we will in this equation of time period, we will use t equals to 2 pi by mass effective divided by spring constant. So it would be equal to 2 pi under root m by 2k. Let's move to the next question. The piston in the cylinder head of locomotive has a stroke of 1 meter. If the piston moves with simple harmonic motion with an angular frequency of 200 radians per second, what is the maximum speed? So here angular frequency, that is omega, is given, that is of 200 radians per minute, and amplitude is given, that is 1 meter of twice the amplitude. So amplitude would be equal to 0.5 meter. Now piston moves with simple harmonic motion, we have to find out maximum velocity. We know that maximum velocity is given as a times omega, or the amplitude times omega, and that would be equal to 0.5 meter, that is amplitude times omega, 200 radians per minute. So it would be equal to 500 meter per minute. Let's move to the next question. In this question, the acceleration due to gravity on the surface of moon is 1.7 meter per second square. What is the time period for simple pendulum on the surface of moon if the time period on surface of earth is 3.5 seconds? So the equation of time period is given as t equals to 2 pi under root L by G for the simple pendulum and for very small displacements. Now if we compare with that of the value of moon and earth, then t of earth by moon would be equal to t by earth by t of moon would be equal to under root acceleration due to gravity of earth by moon. Now if we substitute the values in this equation, we get the time period on moon, and that would be equal to 8.4 seconds. Now moving to the next question. The simple pendulum of length L and having a bob of mass m is suspended in a car. The car is moving in a circular track of radius r with a uniform speed v. If the pendulum makes a small oscillation in the radial direction about its equilibrium position, what would be the time period? So here two forces are acting on the bob. One is the gravitational force and the other is the centripetal force. So since the acceleration due to gravity is not only the acceleration that the bob is facing, it is facing two forces of different magnitude and different direction. So in order to find out the net acceleration due to gravity, we will have to find out the net force, and net force would be given by the vector sum. And since these forces are perpendicular to each other, so we can simply write the net force as the square of first magnitude of first force plus magnitude of second force. Here force is the force of gravitation, and the second force is the centripetal force, that is mv square by r. Now if we single out the mass, so the effective acceleration would be equal to under root of g square plus v square by r whole square, and that will give us the time period, which will be equal to 2 pi under root L by under root g square plus v square by r whole square. Moving to the next question, we have a cylindrical piece of cork of density of base area A and height h floats in the liquid of density rho L. The cork is depressed slightly and then released, so that the cork oscillates up and down simple harmonically with a time period of t equals to 2 pi root under rho h time by rho L g. So here we have to find out we have to show that the cork oscillates simple harmonically and with a time period of 2 pi. The expression is given where rho is the density of the cork and damping has to be neglected over here. So in order to show that the cork is oscillating up and down simple harmonically, we have to show that the restoring force is proportional to negative of displacement, or the direction in which the displacement is happening. The restoring force is proportional to negative in the direction of the displacement. In a nutshell, we have to find out expression for the restoring force. So here, what is the restoring force? Restoring force is the difference between the applied force and the buoyancy force. So applied force is the extra force plus the weight of the body, weight of the cork. Now weight of the cork would be equal to mass times acceleration due to gravity. Now mass, in order to find out the mass, we have to find out the volume, and we will multiply it with the rho, that is the density of the cork. We have been given that density of the cork is rho. So mass of the cork would be equal to rho times A times the height of the object, that is the cork, and the force in buoyancy would be equal to the rho of liquid times area times the dispersed length of the cork. And here initially, since the weight of the cork was balancing the buoyancy force, and then we will get the expression for initial height of the cork, and that would be equal to h naught equals to rho by rho L times h, where h is the height of the cork. Now displacement and the restoring force, when the cork is depressed by a small quantity x below h naught, the new buoyant force would be equal to rho L times A times the depth, initial depth, plus extra depth, that is x, times g. The net force, restoring force F acting on the cork, is the difference between the buoyant force and the weight of the cork, and it is in the opposite direction of the dispersion. So that would be equal to rho L times A times x times g. So this is only the magnitude, and its displacement would be and its direction is in the negative of the displacement. So we can simply write the equation of motion as the net force F provides the restoring force, and restoring force, since it is always in the opposite direction, we can write it as F equals to minus of m times A. And when we write it in this form, then it will relate to the general equation of the simple harmonic motion, that is d2x by dt2 plus omega square x equals to 0. Now whatever the coefficient of x is, that we will term as omega square. Now this omega is the angular frequency. So upon relating it with the general equation, we found out that omega is equals to under root rho L times g divided by rho times h, and which will give the time period as 2 pi times rho times h divided by rho L times g. Moving on to the next question. So in this question, the one end of the U tube containing mercury is connected to the suction pump, and the other end is to the atmosphere. A small pressure difference is maintained between the two columns. Show that when the suction pump is removed, the mercury column in the U-tube executes simple harmonic motion. So here the pressure difference is created initially to disturb the equilibrium of the length of the tubes, and when the suction pump is removed, we have to show that the restoring force is again proportional to negative of its displacement, and we have to show that it is executing simple harmonic motion. So again we will find out the expression for restoring force. Here restoring force would be equal to restoring force would be equal to the difference in the height of the mercury after the equilibrium is balanced. So let us assume that the suction pump sucks the x amount of fluid from one of the tube, so the displacement would be equal to 2x. Now finding out the mass of the displaced fluid and equating it with the acceleration d2 by dx2, we can again relate it with the general equation of simple harmonic motion and write it as d2x by dt2 plus g by h times x equals to 0. Now this equation is in the form of d2x by dt2 plus omega square x equals to 0. So omega is the angular frequency, and this is the standard form of differential equation for simple harmonic motion, where omega is equals to root under g by h. So we can say that it is again executing simple harmonic motion. If you have any doubt, you can ask in the chat box.